Hello everyone and welcome to another video. Today I want to talk about one of the most important concepts in science and engineering, especially in the context of trying to solve ordinary differential equations, and that is the Laplace transform. We are going to see that this is going to be a critical and very helpful way to take functions in the time domain and transform them into an alternate complex domain, or the S domain. So this was invented by the French mathematician Pierre-Simon Laplace. And I think the funny thing that you'll notice is I've seen him referred to as quote-unquote the French Newton. He was very famous. He had a lot of important contributions. The Laplace transform is one of the more significant contributions. So again, Pierre-Simon Laplace is the one that cooked this thing up in the late 1700s, early 1800s. And like we said, what it does, it's basically, you can think of it as a way to take a function in a, say, the time domain. Let's say f of t, it could be cosine of t, e to the t squared, something like that. And what the Laplace transform does, let's just call this like a big black box, and we'll define what this big black box is in a second. But you put in this function in the time domain, and out the other end comes another complex function where instead of time being the independent variable, now you have this complex variable s. Okay? Now, we're going to show exactly what this black box is, but I think maybe one thing that would be helpful is let's take a step back and ask, how is this going to actually help us in the context of trying to solve ordinary differential equations? So let's consider our classic mass spring damper system where you got a mass here sliding in one dimension. Let's measure the deflection from this current position as being positive x of t, right? Now again, the forces that are on this are drawn in blue, so you've got a force u of t that you can apply on here, maybe via an engine or an actuator or something like that. And the block is sliding on this surface which has viscous friction, which we're going to model as cx dot. So the retarding force is proportional to the velocity of the block. So just writing down Newton's second law to get the equations of motion, let's just write that down. So equations of motion via Newton's second law, right? Basically said that what? You got sum of the forces is equal to the mass times the acceleration, right? And remember, mass times acceleration. Acceleration is just the second derivative of position, right? So now what are all of the forces on this block? Well, you've got a positive u of t on one end, and then you've got the retarding force of cx dot. So here's the friction, right? Now, let's say that you want to excite this block or apply a force u of t of, let's pick something. How about u of t, whoops, excuse me, u of t is, I don't know, let's make something up, 3 sine of t. So you're going to apply a sinusoidal force of magnitude 3 newtons, or whatever the unit is, right? So you could rewrite this entire equation here as basically what? 3 sine of t is equal to mx double dot of t plus cx dot of t. Right? So here's your equation of motion. And if you look at it, it's a second order differential equation, right? Because there are two derivatives of the signal you're interested in, right? Usually what we're interested in doing is I need to now find some function x of t that satisfies this differential equation, in the sense that I need to take 2 time derivatives of it, multiply by the mass, add it to 1 time derivative of itself times the damping coefficient, and that better equal 3 sine of t. So how would you do this? Well, there's many different ways to go about this. Let's take a look at the typical slash, maybe let's call it the classical method, right? So typically if someone hands you a differential equation, what you would do here is, well, first thing you're going to do is you're going to start with the ODE, right? So it's in this form. It's basically, it's some function or form. Let's just call it like x dot of t is equal to some function of the x, u, and t, right? That's basically what you've got over there, okay? The next thing that you're going to usually do is, usually this input u is given. So you know how you're going to input what the external inputs to this system are, or how you're going to excite it. So usually, let's just write down that the input u of t is given. Okay? Then the third step you're going to do is, well, now that you've got this forced linear ordinary differential equation, you're going to have to do some things like trying to find a homogeneous and a particular solution, and we're going to go over all of that in another video, but I just want to write down the general procedure here. So what you're going to next do in step 3 is you're going to need to solve for the homogeneous, sometimes also referred to as the autonomous, solution, and the particular solution. And we're going to see later on that step 3, this is actually kind of non-trivial and takes a little bit of black magic a priori knowledge, especially with respect to the particular solution. So this is not entirely great, but it will get the job done. Okay, and then step 4 is once you solve for those, you can basically just add up the homogeneous and the particular solution, and you could obtain x of t. And again, the main disadvantage with this procedure is step 3 is non-trivial, as we're going to see later. Okay. Now, the reason I wanted to write all this down is let's compare this. What can we do with the Laplace transform? We're going to see that the Laplace transform is going to allow us to revise this workflow and come up with a much better way to get to the same solution of basically finding x. So the Laplace method, let's write that down so we can kind of compare and contrast and have a roadmap of where we want to go. So the Laplace method. Okay, what do? You start with the exact same first 2 steps. So this is the same as above, and step 2 is the same, right? You are basically given the same problem. You're given the differential equation, and you're given the input to the system, okay? This is where it diverges, and this is where it gets a lot better, in my opinion. Okay, so step 3 here is you're going to apply the Laplace transform. Okay. To basically both the system and the input. Basically, you're going to apply the Laplace transform to your differential equation, both the left and right side. Okay, maybe let's just say apply Laplace transform to system. Okay, what we're going to see is that this is going to turn the system from being a differential equation to being basically an algebraic equation. So what we're going to end up with here is you can use now algebra to solve for the signal you care about in the Laplace domain. So now you can use algebra to find, I'm going to write it as big X of s, and we're going to see that this is typically the notation where you transform a function from lowercase in the time domain to an uppercase in the Laplace domain or in the complex S domain, okay? And again, this looks a little bit, you're going to have to take my word for it for now, but we're going to see very shortly that this is where all the benefit comes from. Instead of having to guess at homogeneous and particular solutions, you're just going to directly use algebra. There's going to be no derivatives left in the equation. It's just going to be an algebraic equation for X of s, and you can just solve that using things you learned in high school algebra, right? Okay, once you have that, step 5 is going to be, you just now need to apply the inverse Laplace transform. Basically to take the signal from the Laplace domain back to the time domain, okay? So you use this to obtain x of t, which is what you were looking for, right? Okay, so the problem up here where you had a differential equation here is going to turn into something like x of s is equal to some capital F of x and u. And this is algebra, right? There's no derivatives, there's no ddt anywhere. You can directly solve for x here, okay? So that's the beauty of the Laplace transform method. As we're going to see, it's going to take a differential dynamic equation and turn it into a static algebraic equation where you can solve for x of s, okay? So a lot of this, I know you're just kind of having to bleed me right now, but I wanted to lay this out so you can see this roadmap. This is what we're going to go through over the next couple of lectures, is each one of these steps in the process, and we're going to see how it makes solving ordinary differential equations a lot easier, okay? So give me a second, I'll erase the board, and let's finally talk about and define what exactly is the Laplace transform and how do we apply it. All right, so here's the picture we drew earlier, and we said the Laplace transform is really, you can think of it as just like a function, right? A function has inputs and outputs. In this case, the input happens to be a function in the time domain, and it generates a function in the S or the Laplace or the complex domain, however you want to think about it. So let's talk about what goes on in this function. It's just like any other function. You can define it. It's just a routine. It's a procedure. It's an algorithm, however you want to think about it. So the way this works is you take the input. What this function does is it takes the input f of t, it multiplies it by e to the minus st, and then it integrates from time equals 0 to time equals infinity. Sorry, I drew my infinity a little bit funny. Okay? And you basically integrate time away. So you can see that at the end of the day, t is going to be out of this expression, and all you're going to end up with is a function of s. Okay? So this is defined as the Laplace transform of the function f of t in the time domain. This is how you would basically calculate its equivalent in the Laplace domain. Okay, so some alternative notation you might see here is that f of s is equal to the Laplace transform of f of t. So this is just my way, or I guess there's a lot of other people's ways of just writing out and not having to write out this integral every time. So the L and then the square brackets, it's just the Laplace operator where you pass it a function in time, it does this integral, and it will kick out the function in the complex domain. So maybe let's just define all of these so we're all on the same page here. So again, f of t, this here is a function in the time domain. And one thing that we should note here is the lower limit of integration, we're going to integrate from time equals 0 to infinity. So we're going to assume here that this function f of t has the conditions that's such that f of t is 0 for t less than 0. Okay, so it doesn't turn on, quote unquote, so to speak, until time equals 0, which is, I think, a mathematical bookkeeping that really doesn't matter a ton here, but just be important. Just remember, f of t, it's basically some function in the time domain. Cosine t, e to the t, tangent t, whatever you'd like. Okay, so s here is our complex variable. Right, so again, if you would like to brush up on complex numbers or complex variables, please check out our previous video where we discussed complex variables and numbers. Okay, so that's what this s is. It's just a complex variable. We said earlier this L, or I guess L brackets, right? This is the Laplace operator. Now, don't get this confused with Laplacians or other types of Laplace operators if we're talking about differential or vector calculus. We're going to get to that in another lecture, but that's neither here nor there. L in this context is basically this integral, right? Think about it as that integral. And what happens here is at the end of the day, that integral is going to kick out f, big F sub s, right? Which is basically the Laplace transform of f of t. Okay? So there we go. That's what it is. All you got to do is perform that integral. Now, you see integrals and you might ask yourselves, well, is that integral always going to converge? That's probably one of the things you probably want to know about. You might wonder, are there conditions that need to be satisfied in order for the Laplace transform to exist? So in general, one of the things that you can check for here is that we can say that the Laplace transform exists if a couple of things happen. So if f of t is piecewise continuous, in every interval in the range basically of our integration, which is basically t equals 0, okay? Or sorry, t greater than 0. And the other thing that we want here is, or need, is that f of t is of exponential order. Okay? So a function being of exponential order basically means that the limit of this quantity, you take the function f of t, and I guess we look at its absolute value, We just want to make sure it's not going, it can go up to infinity, but basically I can find some other function, e to the minus sigma t. The limit is this, as t goes to infinity, this is 0, or approaches 0, however you want to write this, okay? The limit of this is, right, goes to 0, or is 0. So all this is basically saying here is that, again, f of t can grow, but you can squash it, so to speak, or you can find some exponential, some decaying exponential for some value of sigma. So we should say for an arbitrary sigma. Okay? Basically, this term will eventually squash or destroy whatever f of t is at large values of t here. So again, you can think of f of t here, this can increase, this can blow up here, but you know e to the minus sigma t, what does that look like? That is always some decaying value. Depending on what value of sigma depends how fast this will decay, right? So when you multiply the two of these things together, you should get something that, you know, it might increase when you start, but eventually this exponential will squash it and it'll come back down to 0, okay? So maybe for giggles, let's jump over to Mathematica real quick, and this now might be a good time to plug our video where we discuss 2D plotting in Mathematica, but let's just look at a couple of arbitrary functions just to get a feel for this exponential order. It's not terribly important, but I think it's a nice little side note, sidebar discussion that we can have right now. All right, so let's go ahead and examine some functions to explore the concept of exponential order, right? So again, the idea with the exponential order is, let's look at a function. How about t squared? And let's plot this function over some time range, say 0 to 10 seconds, just to get an idea of what it looks like. So in this case, this function f is blowing up, right? It's increasing to infinity as time goes to infinity. Now the concept of exponential order is, let's consider another function, e to the minus sigma t. Whoops, sorry, I want sigma t. And I want to go ahead and look at, can g of t die faster than f of t grows? So let's plot g of t for some arbitrary sigma value. How about sigma of 1? Okay, and again, let's plot this t from 0 to 10 seconds, same range. Okay, so we see g is dying, f is growing. So the question here in exponential order is the product of f of t and g of t, using, let's say, again, that arbitrary sigma value of 1. If we look at this and plot this over that time range, 0 to 10, does this go to 0 as time goes to infinity? And as you can see, yes, it does. So initially, f is growing faster than g is decreasing, but then at some point, g starts to win, so to speak, and it dies faster. And as time goes to infinity, this function goes to 0, the product here of f of t and g of t. So in this case, we can say that we found a sigma value. Therefore, f of t, the original function, which was t squared, this is of exponential order. Now, we can flip that question around. What if f was different? So example, what if f was e to the t squared? Okay, so now this function blows up even faster. Now, in this case, let's go ahead and look at g of t. Okay, so again, using the same sigma value of -1, it still looks the same. And now let's look at the product. Now, the product here blows up to infinity. Now, the issue here, though, is we don't just want to use a sigma value of 1. We want to look at an arbitrary. Can you find a sigma value? So, for example, let's crank this thing up to 1,000 and enter that again. And look at this. It looks like this is going to 0. In fact, if we look at the product, let me just copy this, paste it down here, and hit enter. And sorry, we should also, let's say, I want to evaluate this at t as 10 seconds, right? That was the end of our window. Look at this. This sure looks like 0 to me, right? Let's go /n. Yep, 10 to the minus 4,300. That is looking like 0. However, the question of exponential order isn't as when t goes to 10, it's when t goes to infinity. So if you look at a larger value of t, okay, that looks like it's now 1. Let's put another 0 in here. Uh-oh, look at this. This thing is blowing up to infinity, all right? Again, you might just say, okay, maybe we just need to make sigma a little bit bigger, right? And now it's back to 0. But again, you can play the same game. As t goes to infinity, eventually this thing is going to blow up. So in this case, you cannot find a sigma value that is going to make the product here go to 0 as time goes to infinity. So in this case, this function is not of exponential order, right? E to the t squared is not of exponential order, and therefore we don't expect it to have a Laplace transform. All right, so we saw that a lot of signals like, e to the something, let's call it minus ct, something like that is of exponential order, so it has a Laplace transform. Things like cosine omega t, right? That thing obviously is of exponential order, so it has a Laplace transform. Heck, multiplying the two of these things together, right? E to the minus ct times cosine of omega t. These things are all of exponential order and therefore have a Laplace transform. And then some things that are not, that don't have a Laplace transform, would be things like f of t, we saw as something like, I don't know, e to the t squared, right? Or things like, do I have another example? Oh yeah, or like how about t e to the t squared, right? Those things are not of exponential order, okay? However, maybe let's make a slight side note. While these are not of exponential order and theoretically don't have Laplace transforms, we can define another function where it's only of this for a certain range and then is 0. So for example, up here in the yes category, you could have a function f of t is, e to the t squared when t is in the range of 0 to some capital T and then 0 otherwise. Right? So this function, it might blow up quicker than an exponential, but then at some point, capital T, it drops to 0. So eventually, obviously, this thing will meet this exponential order condition, and therefore it has a Laplace transform. In general, you can think about this as this is a physically realizable signal, right? One that will explode but then go to 0. That's physically realizable. That might be generated by like an actuator or something like that. It's a real physical signal. Whereas something which eventually goes off to infinity like this is not a physically realizable signal. So physically realizable signals typically have Laplace transforms. That's another nice rule of thumb that we can use. Okay. All right. I think we've got the background of this down. What I would like to do now is let's go through and calculate the Laplace transform for some common f of t's, for some common families of functions in the time domain. What do they look like in the Laplace domain? Okay, so give me a second to erase the board and we'll do the first one with start with an easy one. Let's start with an exponential function. All right, so let's start with the exponential function. Okay. So this is your typical exponential with, I guess, the small modification that we talked about earlier. We're going to assume that this thing is 0 when t is less than 0. But otherwise, it's your typical exponential. Let's make it parameterized with a capital A e to the minus alpha t when t is greater than or equal to 0. Okay, so again, just to get an idea of what this looks like in the time domain, let's try to just sketch this thing out. Okay, so here's t, f of t. Okay, first, you know that it's going to start up here at capital A, right? And depending on what value of alpha you pick, it's going to, for positive alphas, this thing is going to decay, right? So this is in the direction of increasing alpha, right? Okay, so that's what the function looks like in the time domain, right? It's something conceivable, it's understandable, we can plot this out. The question now is, what is the Laplace transform of this function? In other words, what does this function look like in the Laplace domain? Okay, so let's just go ahead and apply the Laplace transform. So in other words, I want to take my function f of t, again, like we said earlier, I want to perform my Laplace operator on it to obtain the function in the Laplace domain, okay? So we said earlier, okay, this Laplace operator, that's my shorthand lazy notation for f of t, right? Here's the function. I hit it with e to the minus st, and then I integrate from 0 to infinity dt, right? Okay, so then for f of t, all I got to do is plug in this. Again, since we're only integrating from time equals 0 to infinity, I don't need to worry about this the condition. So all I got to do is plug in a e to the minus alpha t. So, all right, let's do that right now. So this is now integral from 0 to infinity. Okay, my function f here is a e to the minus alpha t, okay, times e to the minus st dt. right? Okay, a is not a function of time. It's a constant, right? So I can come outside the integral. That's no problem. So I get a times integral 0 to infinity. And then let's just go ahead and combine these exponents, right? This is the same thing as e to the minus s plus alpha t dt. I think everyone will agree I haven't done anything fancy yet. All right, nothing, just combine these two and pull the minus sign out. Okay, this is just your typical exponent, right? So if you recall, let's do the indefinite integral of this first. So the indefinite integral of e to the minus, let's see, s plus alpha t, right? Isn't the indefinite integral of this thing, oh, sorry, dt, right? This is minus 1 over s plus alpha e to the minus s plus alpha t, right? Okay, so here's the indefinite integral. So the definite integral, so I just need to evaluate this at the upper limit minus the lower limit. So in other words, let's jump all the way up here where we get a little bit more room. So I've got a on the outside, right? And then I'm going to have to evaluate this thing from this, right? Here's the indefinite minus 1 over s plus alpha e to the minus s plus alpha t evaluated at t is equal to infinity, right? Minus this thing evaluated at the other limit. So sorry, I'm going to come down here where I got a little more room, right? Minus 1 over s plus alpha e to the minus s plus alpha t evaluated at t is equal to 0. And then n square brackets. Sorry, that's a little bit weird, right? This thing wraps around just because I ran out of room, okay? All right, so let's look at these two terms. Let's look at this term and this term, okay? So the first thing we can do is maybe let's look at this first one. Maybe I will just circle this in blue just so we can kind of see where we want to focus in on, okay? What is this term? Well, you look at this long enough, this is just an exponent, right? Now, the thing that we care about with this exponential is if the real part of this term s plus alpha, if that is positive, you basically have an e to the negative something t, right? So note that if the real part of s plus alpha is greater than 0, this whole thing looks like, this is basically a constant, right? It's just some constant, it's like a beta e to the minus something, I don't know, whatever this number comes at, gamma t, right? This thing, it looks like this, no matter what, right? It might take a while to get there if this gamma is really small, but eventually it goes to 0. So at t equals 0, this whole thing is a big fat 0, right? If this is true, right? So again, this is a minor little note we're gonna have to take into account, but as long as that's true, right? I mean, we make that assumption that this is true, this term goes to 0, okay? Perfect, all right? Now let's look at the other term down here. And in fact, maybe I probably should have grabbed another color. Tell you what, let me erase the blue and I'll move our blue circle so we can evaluate and get a little bit closer to what we care about. Okay, so now focus your attention on the second term. This same thing evaluated at t equals 0. Well, it's still this idea, right? It's still going to look something like this at t equals 0. It actually doesn't matter what the sign, sign is of gamma. This thing is always just going to be a 1, right? So this term right here is basically just a 1. So I got to be a little careful. The exponent part, right? This thing becomes a 1. Right? So all this whole blue term turns into, it's just basically what? It's minus 1 over s plus alpha, right? Okay, so let me erase this to get ourselves a little bit more room. So what this whole thing boils down to here is I still got the a on the outside here, right? And now I've got this whole thing, right? Yes, so this is like a 0 minus 1 over s plus alpha. That's it, right? Because the exponent went to 1. Okay, so great. You boil this all down here, and we end up with this is a over s plus alpha, right? Here we go. I can box this up, and this is what we have. So the original function in the time domain looked like this, right? It was an exponent, an exponential that we were very comfortable with. And now all this is saying here is that in the Laplace domain, this same function, whenever you think a e to the minus alpha t in the time domain, just think about it as a over s plus alpha in the Laplace domain. These two things are kind of equivalent. One is equivalent to the other. It's just looking at it from a different point of view, right? It's like if you see, let me see if I actually have a little prop here, right? You see this guy. Oh man, he lost his cape. Never mind. You know, you don't need the cape. You know who this is, right? You see him normally with your eyes, and and you think Darth Vader, right? Alternatively, if you hear that crazy sound, that's another representation that also maps to Darth Vader, right? So you can think about the two kind of interchangeably. So again, here's the Laplace transform of an exponential in the Laplace domain. Great. Okay, give me a second. Let's erase the board, and we'll do it for another function. All right, I didn't erase all of the board because actually a lot of this is going to be very, very similar. So I'm going to just fill in the blanks where it's appropriate. So the next function I want to look at is how about a step function? So again, it's 0 when time is less than 0, and then it's just going to turn on to a at time equals 0. So again, this is really simple to draw, right? All this thing does here is that it's 0, 0, 0, and then it jumps up to a constant value of a and stays there forever, right? So that's what this function looks like in the time domain. So again, the Laplace transform method is a very similar process, right? Just plug it into the definition of the integral and start cranking away. So, all right, let's go integral 0 to infinity of a e to the minus st dt. Right? Okay, this is basically the exact same thing we did earlier. So you're going to recall here that, okay, the indefinite integral of e to the minus st dt is just negative 1 over s e to the minus st, right? Okay, so then evaluating this thing at our two limits, right? Let's pull a out, and then we're going to have negative 1 over s e to the minus st evaluated at t equals infinity, right? Minus negative 1 over s e to the minus st evaluated at t is equal to 0, right? And I guess we can change these double negatives, so I'll just make that a plus. Right? Again, we make the exact same argument. In this case, it actually doesn't matter here. This is going to be 0, right? So this whole term goes to 0. The exponent here goes to 1. So actually, so let me just draw just the exponent part goes to 1. So we're ending up with, at the end of the day, this is all just a over s. So here's f of s. Great. So a step function, right, looks like that in the time domain, but it looks like this in the Laplace domain. So there you go. The other way you could think about this is, if you remember earlier, we showed that the Laplace transform of a exponential function, right, the one we just did earlier, right, of a e to the minus minus alpha t, right? This was a over s plus alpha, right? Well, isn't a step function, it's basically an exponential function when alpha is 0, right? So note that a step is it's a special case, it's a special type of an exponential where alpha is equal to 0, right? So look at that, right? A over s plus alpha, if alpha is 0, you end up with a over s. So that also checks out. So again, there's more than one way to skin a cat here. You can get to the same result multiple ways. So again, long story short, the Laplace transform of a step input is a over s. All right. On to bigger and better functions. How about a ramp? So the ramp is actually pretty simple. Let's make it a ramp with slope a. So again, this thing is just 0 until times t equals 0, and then it slopes up at slope a. Okay, so there's our function f in the time domain. So again, let's just run through our procedure of taking its Laplace transform. So okay, here we go. So integral 0 to infinity of the function, which is at e to the minus st dt. Okay, again, a is not a function of t, so let's pop it out of the integral. So I can write this now as a integral 0 to infinity t e to the minus st dt. Okay? All right, so at this point, we are a little stuck here until we go ahead and remember our integration by parts. So let's do integration by parts. So just to refresh your memory, right? Integration by parts was saying if you had integral of u dv from the range a to b, integration by parts said that was the product of uv evaluated from a to b minus the integral of v du over that same range, or that same limit of integration. Okay, so we just need to choose u and v appropriately. So in this case, let's go ahead and choose, how about u is going to be t. So if that's our choice of u, that means du is just going to be dt, right? Just take the derivative. And let's pick dv to be the term e to the minus st dt, right? That's the rest of the thing that we like. So if that's our choice of dv, that means that v has got to basically be the integral of this. So v has got to be negative 1 over s e to the minus st. Right? That's a consistent choice. Okay, so now just plug all of these into our integration by parts, right? Because we see that this left side, this term is basically this exact integral that we have here. So in this case, yeah, u is t, dv is the rest of it, and we see a is 0 and b is infinity. Okay, great. Just plug it into our expression. So what we end up with then is that we can rewrite this whole thing. We have a, and I'm going to now rewrite the integral here using our integration by parts. So I'm going to plug in the left-hand side. So what is u? U, we said this is t times v. Where's v? Here's v. So this is times negative 1 over s e to the minus st. This whole thing is evaluated from a to b, right? Oh, sorry, and now instead of a to b, in our case, a was 0, b was infinity. Maybe we should have written that here. Maybe, yeah, I ran out of space. Okay, a is going to be 0, b is going to be infinity, right? That's our limits of integration here. Okay, so sorry, I got a little sidetracked. That was this first term here. Now minus the integral from 0 to infinity of v. Where's v? Here it is. Minus 1 over s e to the minus st du, which is right here, which is just dt. There we go. Okay. That's how we rewrote this thing using integration by parts. So let's first go ahead and again, maybe I'll use my blue pen, and let's examine this term right here. Okay? So if you look at this long enough, and if we assume that s is basically positive, right? So if s is positive, right? What does this e to the minus st look like? Again, it's an exponential. Right? And again, we're not going to have a divide by 0 problem here. So this function right here, we got to look at it, this whole thing, t times basically an exponential at t equals infinity, right? That's the upper limit. So maybe we should write this thing out. So let's write out the blue term here. So the blue term, it's t, or I guess it's negative t over s e to the minus st, right? Evaluated at t is equal to infinity minus, I guess, plus evaluated at t equals 0, right? That's the blue term, okay? So if s is greater than 0, let's take a look at this. What is this term right here at t is equal to infinity? Well, you can look at this and remember our discussion of exponential order. We know the function t, it's just a linear, it's of exponential order. This exponent is going to crush it. Even though t is increasing, e to the minus st is going to decrease as time equals 0. So this overall product, it's going to go to 0, right? This is eventually going to be 0 at t equals infinity, okay? Let's look at the second term. When t equals 0, what does this look like? Well, when t equals 0, the exponent here just becomes 1, and then t equals 0. So look at that. You got 0 times 1, so this whole thing becomes 0. So in other words, this entire blue term is a big fat goose egg, right? That is 0, okay? Great. Now we just got to deal with this. So tell you what, let's come over here and rewrite this when we get ourselves a little bit more room. I guess I'll come over here. Okay. So we're left with, again, we're still trying to find the Laplace transform f of s, right? And now we've shown that this whole thing looks like an a times the whole blue thing went away, and I guess now the positive, the negatives cancel each other, so we end up with this is just 1 over s, integral from 0 to infinity of 1 over s e to the minus st dt, right? Great. Okay, s is not a function of t, so it can come out of the integral, so this whole thing can be a over s times integral from 0 to infinity of e to the minus st dt. You know what? We've done this a couple of times already, right? This is just an integral of e to the minus st, so this is going to be, let's just go ahead and do this. So when we, let's see, we get, this is minus 1 over s e to the minus st, right? I think so, yep. Evaluated between the limits of 0 to infinity, right? That's what we end up with for that integral, okay? All right, I guess maybe we should have broken this out. Let's break this out into the two terms again so we can look at them. So this is minus 1 over s e to the minus st evaluated at t equals infinity minus a negative 1 over s e to the minus st evaluated at t equals 0. Great, again, so let's bust out our blue pen and isolate these. So you'll look at this term first, right? We already made the assumption that s is greater than 0 back here. So this term, right, at t equals infinity is a big fat 0 again, right? This is 0, okay? Now let's move our blue penish again to this second term, and specifically, all right, and now I want to look at this term, okay? Same thing, you look at this, s is not going to be 0, right? We made that assumption, and we said s is positive. So really, at time equals 0, the exponent goes to 1. This negative cancels with that negative. So this whole thing becomes basically what? This term, it turns into a 1 over s, right? Great. So at the end of the day, what we end up with is, shoot, well, let's just write it out. Let's just write it here. Right? So f of s is equal to a over s times this whole thing in square brackets is just a 1 over s. So you end up with a over s squared, right? So again, a ramp in the time domain looks like an a over s squared in the Laplace domain. All right, so let's get to some interesting ones. How about a sine or a cosine function? So let's use sine for example, maybe like an a sine omega t, right? Everyone knows what that looks like in the time domain, right? This is just a sinusoid of magnitude a and angular frequency omega. So actually, I'm not going to go through the entire derivation of this because I use it in a homework assignment. So you'll definitely do this in a homework assignment. Maybe just to give you a little bit of a hint, what I would recommend doing is trying to remember that you can use the relationship between the definition of a sinusoid and the Euler formulation of said sinusoid, right? Where you could express a sine wave as a summation of a bunch of exponents. So in other words, just to be explicit, maybe we'll do it for sine. This would be a times, sine omega t. Again, you could use Euler's formula to basically write this thing something like e to the j omega t minus e to the minus j omega t all over 2j, obviously where j is the imaginary number. Right, this is the same thing. And now if you plug this into your definition of the Laplace transform, you can kind of see why this is going to get a little bit easier, where you can have exponents. And again, if you just turn the crank and work your way through this, I think you can end up with, at the end of the day, a result. Maybe, tell you what, just for giggles, I'll go ahead and write it down here. So f of s for a sinusoid, this is going to look like a omega all over s squared plus omega squared. Just double check, make sure I didn't mix that up with the cosine. Yeah, that should be right. There you go. So again, here's what a sine wave in the Laplace domain looks like. Okay, and again, working on all this through is in a homework problem. Okay, all right, let's keep going. All right, so now let's take a look at a more abstract function, namely a translated function. So what I want to do here is instead of f, let's consider a function g, which is basically a function f, but it's translated or time delayed here by alpha seconds. Okay, so, and this is for t greater than alpha. Okay, so what this looks like, just so we're all on the same page, is let's just plot this out. So here's f, oh, whoops, sorry, this is the independent variable t, and then you've got the dependent variable, which is going to be f of t or g of t. In this case, we're going to plot both of them. So let's first look at f of t. So f of t could be, you know, something like a sine wave. Something like this, okay? And what g of t is, it's basically the function value of f, but it's delayed by alpha seconds. So basically, what g is going to look like is, okay, it's going to be 0 until you get to alpha, and then it's just going to be basically this function now translated. So it's going to be time delayed. So what that would look like is now it does something like this. Right? So this distance here, or this delay, is alpha seconds, if you want to think about it that way. Okay, so the blue is g of t, and the black is f of t. And again, this holds for any function. I just happen to draw a sine wave because I think it's easy to sort of visualize, but the concept here is I want to look at what is the Laplace transform of the blue function it related to the Laplace transform of the black function, or the original function, right? So again, we just need to run through our procedure, okay? So the first thing I want to do is, let's think about this a little bit. I want to rewrite g of t. So g of t, again, let's write this down. So g of t is going to be f of t minus alpha. Whoops, let me make this a little bit more clean. F minus alpha. Right? And it doesn't turn on until alpha. So really what I could do without any other consequences is I could say this is multiplied by a step function, a unit step. So I'll write it like this, which turns on at alpha, at t equals alpha seconds. So again, all this function here is, I probably should have talked about this a little bit when we were talking about a step function. You remember we had a step function of magnitude a, and we showed that its Laplace transform, well, I think it was a over s. This is just a step function of magnitude 1 here. So all this thing is, it is 0 until the argument here becomes positive, then it jumps up to 1. So really, it's just like adding a 1 to this signal after alpha seconds. So really, this is the exact same thing. I haven't changed anything. This is going to make our lives a little bit easier, okay? So again, let me just explicitly label this. This is a unit step at t equals alpha, right? That's how you can think about this second term. Okay, so plug this into, well, I guess we got to change all this. We're not looking for the Laplace transform of f anymore. I want g, right? Right? Okay, so all we got to do, plug this in to here. So we end up with integral from 0 to infinity of f of t minus alpha times a unit step of 1 minus alpha times e to the minus st dt. Right? I think I got that. Okay. What I want to do now is I want to make a change of variables of integration. Okay, so let's change the independent variable. Okay, so I want to change it from t to changes from t to, I want this to now, our independent variable to be tau, and that's going to be related to t through basically t minus alpha. Okay, so therefore what we're going to do is we're going to have to change the limits of integration. So let's take a look at that here. So the lower limit, right? Earlier, what was our lower limit of integration? It was t equals 0, right? So now how does that relate to what is the limit on tau? Well, you can look at here, this means tau is equal to minus alpha, right? So just plug in t equals 0. Okay, so the upper limit earlier was t equals positive infinity, okay? So again, plugging in positive infinity into this expression, what do we end up with? We see that basically tau is, well, that infinity is going to swamp it, so we end up with tau is equal to infinity as the equivalent, still the equivalent upper limit, right? Okay, great. So now let's just make this change of limits of integration, and we can change the independent variable in here. Okay, so our integral here, maybe let's write it down here so it's all in one place and we can easily compare. Okay, so this is now, the lower limit is now minus alpha, and the upper limit is still positive infinity. And now f of, okay, now I can just write this as f of tau, right? This is f of tau times a unit step of tau, right? Times e to the minus s. Okay, now t. I gotta switch in t. T is actually what? It's tau plus alpha, right? So this is tau plus alpha. Okay, d tau. Okay, so all I've done here is just change the independent variable and therefore the limits of integration. Okay. All right, let's tell you what, let's break up this integral to go, instead of going from minus alpha to infinity, let's go from minus alpha to 0 and then from 0 to positive infinity, okay? So in other words, let's come up here, maybe I can get a little bit more room. Okay, so I can write this thing as integral minus alpha to positive infinity f of tau times unit step tau e to the, make sure I have this consistent with how I wrote my notes out, right? Negative s tau plus alpha d tau. Okay, that's the first limit, or the first region from minus alpha to 0. Now I got to add this thing to 0 to positive infinity of f of tau times a unit step tau e to the minus s tau plus alpha d tau. Okay? So, sorry, I ran out of room. It's this term plus this term is the exact same thing there. We just broke up the integral to go into two different sections, right? Okay, now, what's helpful about this is, let's look at this first integral, okay? When tau is between negative, oh, whoops, sorry, that should be up with 0. Whoops. There we go. Okay, there, that's better. Because in this region, when tau is negative alpha to 0, this unit step hasn't turned on yet, right? So this, in this region, this is 0, right? Which knocks out this entire term. So this entire integral here is a big fat 0, right? Because the unit step hasn't turned on. So we're just left with this single term, right? Okay, so yeah, maybe here, let's erase this and we'll rewrite it over here, okay? Okay, so we now have g of s, right? This is what we're looking for, is now just that second integral, right? So the integral from 0 to infinity of f of tau times, oh, and I guess the other thing we could also notice is in this time integral from 0 to infinity, what has this unit step done? It has turned on, right? Because now tau is always positive in this case. So this is basically a 1. So I don't even need to write this unit step any longer. Let's just get rid of it. So what I can just say is that's just f times e to the negative s tau plus alpha d tau. Right? Okay, let's break up this, this exponent a little bit. Integral from 0 to infinity f of tau times e to the minus s tau times e to the minus s alpha d tau, right? Okay, let's examine this closely. F of tau, that is clearly a function of tau, so I can't pull it out of the integral. This is a function of tau, so I can't pull it out of the integral. This is not a function of tau, right? This is e to the minus s alpha. That can come outside the integral. So we end up with here, this is e to the minus, actually let's write it alpha s. I'll just switch the order. It doesn't really matter of the exponent, right? Times 0 to infinity f of tau e to the minus s tau d tau. Right? Great. Now, if you look at this integral here that I'm going to box up in blue, in dashed blue, this ought to look really darn familiar, right? This thing looks like a function. You multiply it by e to the minus st, and you integrate from 0 to infinity to get out the independent variable here. Which, you know, this could be tau or this could be t, right? We could just change the notation if you want. What is this? This is the friggin' definition of the Laplace transform of f, right? So this whole thing in blue, this is f sub s, right? It's the Laplace transform of the original untranslated function you're looking for, we started with, right? So let's boil this down to, at the end of the day, what did we end up with? So we end up with g of s is equal to e to the minus alpha s, right? Where did I? Yeah, perfect, right? Times f sub s, right? So look at this. This is actually a really fascinating result here. Because what does this mean? If you remember, shoot, I erased the picture here, right? But here's the original picture we had. Here's t. Here's the original function f, right? And then we had our translated function, which was delayed by tau seconds, and it didn't turn on until tau. Sorry, alpha. Sorry. Sorry, okay. Alpha was our time delay, right? So here's alpha, right? So the blue here is g of t. The black was f of t. So let's just examine what this is. So this time delay of alpha seconds, this is what it manifests itself in the Laplace domain. So a pure time delay of alpha seconds looks like an e to the minus alpha s in the Laplace domain here. So again, this is really powerful because it says if you know the Laplace transform of your function, it can be anything. It could be the sine, it could be the ramp, it could be the step function, the exponent, any of these things we talked about previously, right? If you want to time delay it, have a pure time delay of alpha seconds, all you do in the Laplace domain is multiply by e to the minus alpha s, right? And that is a pure time delay, right? So this is really, really handy, right? So maybe just to drive that home, all right? Let's just look at a quick example. Okay, so what was one of our things we had? Like a let's do the exponent. Remember, we had f of t was something like e to the alpha t, or where I don't want to mess this up. I want to make sure my notation is the same that we had earlier. Oh no, sorry, it was a e to the minus alpha t, right? This was our exponent function, right? So this was something like starts here at a, decays down, something like this, right? Here's f of t, right? And we know that this thing's Laplace transform was a over s plus alpha, right? Now, if I want to time delay this thing and have this thing start like alpha seconds later, just be delayed. So here's my blue is g of t, okay? I now know that g of s, right? It's just the original thing that I had, right? A over s plus alpha. And now all you have to do is multiply it by e to the minus alpha s. And here we go. This, in the Laplace domain, is a time-delayed, shifted exponent. So there you go. So this is actually pretty fascinating. All right. Give me a second. I'll erase the board, and let's go on to another type of function. All right. How about a pulse function? So what a pulse looks like is, again, it's basically 0, and then it's going to turn on to a value of a over t naught when t is actually in the range of 0 to t naught. Okay? So, and I guess maybe we should just say this is otherwise, I guess. All right, that's a lot of definition. I think it just makes a lot more sense if we just plot it and draw it. So let's do that here. Okay. So again, all this thing looks like is it's 0, 0, 0. Then it's going to jump up to a value of a over t naught for t naught seconds, and then back down to 0. So this distance here is t naught. So you see that it's basically just here a pulse of distance t naught, and the area under the curve of this thing is basically just a. Okay? Now, the reason I wanted to do this, I wanted to wait to do this one until we had done the translated function, is because if you think about this long enough, this is actually, you can think of this as the superposition of two step inputs. So this thing is equal to, I can add up two step functions. So let's do this. Let's draw it underneath of it. Oops. Sorry, this is probably a little bit hard to see. Okay, like this here, here's t. So here's step one. One of them just comes here and then turns on to a value of a over t naught, right? So here's like f1, right? This plus a second step function, which is basically 0, 0, 0, 0, 0, and then here at t naught turns on to a value of negative a over t naught, right? Wouldn't you agree that if you took this pulse, or sorry, this step plus this step equals this pulse, right? So mathematically, right, couldn't we write this as f of t is basically, it's what? It's a unit step which turns on at time 0, right? But it doesn't go to a unit step value, right? It goes to a value of a over t naught, right? Plus, here's a time delayed unit step, right? It's time delayed by tau seconds, or sorry, t naught seconds, right? So here is a unit step that is time delayed by t naught seconds. And again, it doesn't go to a unit step value of 1, it goes to a value of negative a over t naught. So this is negative a over t naught, right? There you go. So it's basically, it's a function added to a time delayed function. We can just spam the rule we just developed for time delayed functions. So to get the Laplace transform of this, I actually don't even need to really go through cranking through an integral, because what we could do is we could say that, okay, the Laplace transform of this, right? I'm just plug in this whole expression into here. So we end up with, this is the Laplace transform of this gobbledygook, right? A over t naught unit step t minus a over t naught unit step of t minus t naught, right? So you know this Laplace transform operator, it's an integral, right? So this minus, I could just distribute the integral through, or what you could do is I could just say this is Laplace transform of a over t naught unit step t minus Laplace transform of a over t naught unit step t minus t naught, right? And again, remembering that this Laplace operator is my lazy-handed way of not writing out that integral blah 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 e to the st dt, this coefficient is not a function of t. This t naught is a constant, right? So again, this can come out of the integral. Same thing here. This can come out of the integral. So I could even simplify this one more step, right? So this is a over t naught Laplace transform of a unit step minus a over t naught Laplace transform of a time delayed unit step, right? So okay, this is easy. We already did a unit step, right? We know that this now, I got a over t naught. So the Laplace transform of a unit step, we did that earlier. This is just going to be 1 over s, right? Wait, did I? Yeah, I just want to double check, make sure I didn't mess it up. Yep, okay. Minus a over t naught. Here's this. Now I got to do this Laplace transform. And again, this now is what we just talked about earlier. This is a unit step, but it is time delayed by t naught seconds. So the Laplace transform of a plain old unit step is this thing, right? And now to time delay it, we just use the expression we talked about earlier. Well, you hit this with a e to the minus t naught s, right? There we go. And we're almost there. So now maybe let's just clean this thing up and simplify it a little bit. So I think I could write this whole thing as, yeah, all these come out. Okay, so it's a over t naught s times 1 minus e to the minus t naught s. There we go. So here we go. So here is the Laplace transform of a pulse right over there. And again, you see, we didn't actually have to crank through any of the integral because we can start making some of these arguments and spamming and reusing some of those results we derived previously to get to this result. Okay, let's do another one. Instead of a pulse, how about let's look at an impulse next. All right, so the next one I want to look at, and I didn't erase the board because the one I want to look at now is an impulse, not a pulse. And an impulse we're going to see is really just a special case of a pulse. And all it's basically saying is it's a pulse, but we're going to let this delta t go to 0. So maybe a better way to write this is f of t is basically this thing with the limit as t naught goes to 0. Okay, so basically it's just shrinking this, but we're keeping the area under the curve, quote unquote, equal to a. So you can see that as t0 gets smaller, basically this thing gets bigger and bigger and bigger, and it's basically it starts becoming this mathematical fantasy here, right, rather than a physically realizable signal. But nevertheless, that's all it is. It's basically take the limit as t0 goes to 0. So all of our discussion with the pulse holds until we get down to here. So it's basically looking at the limit of this as t goes to 0. So the only problem here is if we take the limit of this as t naught goes to 0, right? You look at this, we end up with 1 minus basically a 1. So we get a 0 in the numerator and we get a 0 in the denominator. So we actually have this indeterminate limit. So we actually need to apply, if you remember, L'Hopital's rule to solve this, right? So note that we have an indeterminate limit of the type 0 over 0. And remember, if you have something that is indeterminate of the type 0 over 0 or infinity over infinity, right, we can apply L'Hopital's, make sure I spell him right, rule, right? So what that basically said is L'Hopital's rule was if you have the limit as t goes to a or something like that of g of t over h of t, right? A numerator over denominator, and this is of this form 0 over 0 or infinity over infinity. L'Hopital's rule says that this limit is the same thing as the limit as t goes to a of basically taking the derivative of this, right? Of both the numerator and the denominator with respect to the independent variable, okay? So applying this to our system here, we basically need to take the derivative of this with respect to t0 here, right? Because that's the thing that's going to infinity, right? T here. Okay, so applying this, we basically have, now we have to take the limit as t goes to, oh sorry, nope, t0 goes to 0 of, let me just write this thing out. So we got the numerator here. The numerator is what? It's a times 1 minus e to the minus s t0. So t0 in this case is sort of our independent variable. So I need to take the derivative of this or the partial of this with respect to t0. Right? That's this first term, this g prime. And then the denominator, what's our denominator? It's t0 over s, or t0 times s. So again, I take the partial of this thing with respect to t0, which is my independent variable. There we go, okay? So let's do this. So what do we end up with at the top? If we take the derivative of this with respect to t0, what do we end up with? We end up with the numerator looking like a s, yeah, right, the s drops down, right? S e to the minus s t0. Right, did I drop negative sign? See, I take 1? No, because the negative's right here, right? You take the 0. Yeah, yep, this is what you should get on the top, right? And then the bottom is just s, right? There, okay. So, and then again, we probably should have kept the limit on the out of this. Sorry, I should have written limit as t0 goes to 0. Okay, great. So now these cancel. So we end up with limit as t0 goes to 0. So we end up with a e to the minus st0. There we go. Okay, now we can evaluate this, and we end up and we see that as t0 goes to 0, this exponent just goes to a 1. So we end up with just a. So here we go. So f of s, this is what an impulse in the Laplace domain looks like. So again, this mathematical fantasy over here, where in the time domain it corresponds to this infinitely high spike, but happens to have this area under the curve of 1, area under the curve of a, looks just like a in the Laplace domain. So again, I want to drive this home because we're gonna take a look at this later in the sense that this is this. We've sort of left the realm of reasonable signals, right? A pulse is totally fine, right? A pulse is if you had, like, for example, let me see. Oh, yeah. Like I got a little car here. So, you know, if you had a little car and you were interested in applying a pulse in thrust to the car. So that would just be you push on the back of the car and for a finite amount of time, t0, but you push with a finite amount of force being a over t0. That was a pulse. Now this impulse is, instead of pushing for a finite duration, you're pushing for an instantaneous amount of time, for an instantaneously short amount of time, but you're cranking that up, right? The value, the amount of force is a lot. So it's again physically unrealizable, but you know, a good approximation might be like if you hit something with a baseball bat, right? That imparts this short amount of energy and force, but for a very small short amount of time. And you can see why this is kind of ridiculous from engineering perspectives. It's a nice mathematical concept, but if you were to do that to a real system, right? It doesn't really work very well. So keep that in mind. Impulses are not really physically realizable, but pulses are. So actually, before we leave this discussion on the impulse, I wanted to make a quick comment here on the lower limit of integration. So the reason this is sometimes brought up is, although we just discussed that this impulse is kind of a mathematical fantasy, sometimes they are useful. And sometimes you'll have a function, f of t, which actually has an impulse at time 0, right? That's basically the idea with an impulse, is it's this action that happens right here at time 0. So maybe what we should do is we should be a little bit careful about, if we're talking about the Laplace transform of some function f of t, right? This usually, right, is defined as from 0 to infinity, as we said. It's the function times e to the minus st dt, right? But now we got to be a little bit careful. Do we mean this 0 is from the left or the right-hand side, right? Because now in this case, when we're dealing with an impulse, that might matter. So for example, if we denote L minus as being from the 0 minus side, then maybe we can also define L plus, right, as being the same thing, but the lower limit of integration starts from the plus side or to the right side of the 0, right? F of t e to the minus st dt, right? So let's take a gander at it. Maybe let's look at this first expression here, this first derivative, integral, especially with respect to the limit of integration. So this first one, right, notice that you could write this thing out as, okay, let's go from 0 minus up to 0 plus, right? F of t e to the minus st dt, right? And then we'll go from 0 plus all the way up to infinity of the same thing, f of t e to the minus st dt, right? That's the exact same thing. Now, for most parts, you would say, this is nothing, right? You're integrating over from 0 minus to 0 plus, so over this infinitesimal time window, where that's going to be, usually it's going to be nothing, right? Because this function value over that tiny little measure of integral is effectively 0. In almost every single case, except when you have an impulse, because we know that if f of t has an impulse right there at that time, right? We said the Laplace transform of an impulse was a. So this here is not equal to 0, right? If the system or the signal has an impulse at time 0. So if that's the case, you can clearly see that, well, this definition over here, right? This is the Laplace plus, right, of f of t. Right? That's that definition right here. And the left-hand side was L minus. So we see in this case, again, if you have an impulse that occurs at time 0, the Laplace transform from the negative side of 0 is not equal to the Laplace transform from the positive side of 0. So this is one thing to maybe think about, that when your signal has an impulse in it, you got to be a little careful on the lower limits of integration in terms of what are we actually talking about. So again, This is a little bit of a detour, a little side note. Again, I think this is a little bit of a mathematical fantasy. I keep wanting to call it that, but again, it does show up, so I think we should be cognizant of this fact. Okay, so that being said, let's move on to another function. All right, so let's move on to another class, which is multiplication of a function by a very specific type of other function, namely e to the minus alpha t, okay? So in this case, what I'd like to consider is a function, let's call it g of t, which is some other function f of t, but then you multiply it by e to the minus alpha t, okay? Something like that. Now, you might think this is pretty esoteric and something you might not ever need to deal with, but this actually shows up all the time. So, especially for those of you studying ordinary differential equations and dynamic systems. So, for example, let's consider some function f of t as maybe just being like a cosine wave, right? So this black line is f of t, which is a cosine omega t, right? So all this thing does is it oscillates between a and minus a with some angular frequency omega. Okay, now what you might want to do is, why don't we go ahead and let's consider another function. How about this g of t, which is going to be e to the minus alpha t times this function that we already talked about, a cosine omega t. Right? So what you can do is you can kind of think about this as this e to the minus alpha t basically makes the cosine wave either decay or exponentially explode. So in most cases, alpha is positive, so this would be a decaying cosine wave. So instead, what g of t is going to look like is it's going to look like this, and it's going to actually start decaying, something like that. Okay? And this decay curve is this exponential here, right? So this here is e to the minus alpha t, right? And the overall blue line is now this g of t function, okay? So again, this shows up all the time, okay? So let's go ahead and see, is there a way that I can relate the Laplace transform of the black line to the Laplace transform of the blue line, which is what I want, okay? So let's just go ahead and recall the definition of the Laplace transform. Right, so we said that, okay, the Laplace transform of some function f of t, right? This is just going to be integral from 0 to infinity e to the minus s, the function f of t, right, times e to the minus st dt, right? So this here was f sub s, right? So we should pretty much immediately follow that, okay, instead of using a variable s as the input argument, how about I use s plus alpha? So in other words, I want f of s plus alpha. Okay, so the way you get that is basically you take everywhere you see an s and you replace it with s plus alpha. So on the left side, or sorry, on the right side, this now becomes 0 to infinity of f of t, e to the minus, now I got to replace s with s plus alpha t dt. Okay, let's box this up and call this thing equation 1. Okay, we're going to use this in a second. Okay, all right, so via another independent line of reasoning, let's go ahead and just write out what is the Laplace transform of g of t. Right, so in other words, I want the Laplace transform of this function g of t, right? Which is basically you take the function g of t, you hit it with e to the minus st, and you integrate from 0 to infinity dt, right? Okay, we know that g of t is e to the minus alpha t times f of t, right? So the Laplace transform of e to the minus alpha t f of t, right? It's just, okay, it's now this, so g of t is e to the minus alpha t f of t, there. Then I multiply by this one, e to the minus st, and I integrate from 0 to infinity dt, right? And notice now I can combine these exponents to basically end up with 0 to infinity f of t e to the minus s plus alpha t dt, right? So this is Laplace transform of e to the minus alpha t f of t, right? Great, box this guy up, call this thing equation 2. Okay, now if you look at equation 1 and equation 2, the right-hand sides are identical, right? So therefore, the left-hand sides have to be identical. So this immediately follows that we can say that, okay, Laplace transform of e to the minus alpha t, f of t, is equal to f of s plus alpha. And this is the result we're gunning for. This is very powerful, right? It says that if you have a function f of t, and I already know what its Laplace transform is, it's capital F, right? And now all I want to do is have this thing exponentially decay or exponentially increase. Instead of putting in s as the argument over here on the Laplace side, you put in s plus alpha, all right? So very powerful. Let's go ahead and come back to our example of the cosine wave to apply this rule. Maybe let me erase all this so I can get a little bit more room to apply the rule. I'll leave our rule up so we can go ahead and use it, okay? So coming back to our example, what I want to do is I want now the Laplace transform of e to the minus alpha t times a cosine t here, right? Okay, and we want to say, what is this? So instead of going through the rigmarole of actually trying to do that integral manually, let's just spam this rule. So what we need to do is first, let's recall, what is the Laplace transform, or sorry, what is, well, I guess we could have written it that way, sure. Laplace transform of f, right? Which is the Laplace transform of a cosine omega t, right? That's the original function. And if you remember, this is exactly what we did a couple of examples ago, right? We said that this is just as over s squared plus omega squared. Okay? So now, by applying our rule, right, this right here, this is f sub s. Right? Now, if I want to make this cosine wave just exponentially increase or decrease, all I have to do is just plug in everywhere I see an s, put s plus alpha. So just to be explicit about that, so now Laplace transform of the thing I want, a cosine omega t, right? Now multiplied by e to the minus alpha t, right? It's just this. Everywhere you see an s, replace it with alpha, s plus alpha. So now it's a s plus alpha all over s plus alpha squared plus omega squared. So there you go, right? So instead of having to do all of that actual integral, you can just apply the rule and we're off to the races. All right, so now we come to the most important one of these rules that we're going to talk about today. So if you've zoned out for the past 20 minutes or the other ones didn't seem particularly interesting, please pay attention now because this is super, super important and very, very helpful when dealing with differential equations. Okay, so this here is what's called the differentiation theorem. Basically, what we're looking at here is I want the Laplace transform of a derivative of a signal. That's what we're gunning for. So what I want is some expression, Laplace transform of, say, f prime of t is equal to something, right? How can I get the Laplace transform of the derivative of one signal, okay? So to do that, let's go ahead and first just rewrite the definition of the Laplace transform. And we've done this so many times, I think you guys are very familiar with this, right? So the Laplace transform of just some signal f of t, right? This is going to be, well, it's the function, then you hit it with e to the minus st, and you integrate time out of here, right? You do something like that, okay? Now, let's just leave this definition here, and again, let's recall our differentiation, or sorry, the integration by parts. Right? We already spammed this one other time, but I'm going to write it up here just for completeness, right? So we said, okay, you got the integral of u dv from a to b, right? This is equal to uv evaluated between a and b minus the integral of v du from a to b, right? Okay, so let's choose for this particular case, let's go ahead and make these substitutions. How about, let's consider u of t to be the function f of t, right? If that's the case, then du, right, this is just going to be f prime, right? Its derivative dt. right? I just take a derivative of this one time, I get f prime t dt. Okay, and let's choose dv to be the other portion of this part, right? So this is going to be e to the minus st dt, right? If this is our choice of dv, that means that v has got to look like, what is it? It's minus 1 over s, right? Minus 1 over s e to the minus st, right? And obviously, we see our integration limits. A is 0, b is infinity. Maybe we should just write that down for completeness. A is 0, and b is infinity, right? Okay, plug all of these in to our integration by parts, and what do we end up with? So we end up with, let's see here. Okay, so the left side is basically what we're looking for, right? So the left side becomes integration from 0 to infinity of u, which was f of t, and then dv, which was e to the minus st dt, right? So good, the left side is totally fine, so we matched up the left side. Now, here's where we're going to apply integration by parts. This is what it should equal according to integration by parts. So it's u times v, where's u? Okay, there it is. It's f of t times v. I want to make sure, yeah. Where's v? Right here. Times negative 1 over s e to the minus st, right? Should be this thing all evaluated between 0 and infinity, right? Minus the integral from 0 to infinity of v du. Where's v? V is right here. So this is minus 1 over s e to the minus st, right? And then v du, I need du, which is right here, times f prime of t dt. Okay, did I get all that right? Well, I'll tell you what, let's simplify this a little bit, okay? So, let's see here. So we can write this thing out in two parts. So this is f of t, and I guess there's a negative here, over s e to the minus st, evaluated at t is equal to infinity, right? Minus, I guess this is now f of t over s, and there's another minus here, so I'll tell you what, let's make this a plus and make that a plus, right? E to the minus st evaluated at t is equal to 0, right? That's the first part, minus this integral here. So we end up with integral. Now look at this, the 1 over s, this is not a function of t, right? So it can come out of the integral. So actually that is going to make it a plus 1 over s on the outside from 0 to infinity of f prime of t e to the minus st dt. Okay, there we go. I think that's pretty reasonable. Did I get all that right? Minus ft s e to the minus st t equals infinity. Yep. Plus ft t equals 0. Yep. Yep. All right, great. Yeppers, that's what we're looking for. Okay, now let's look at each one of these terms one at a time. Okay, so let's look at this first term here. Okay, what is this? Right? You might want to think, okay, what do these look like? E to the minus st, right? Again, assuming s is positive here, right? This e to the minus st is a decaying term, right? What does this look like? Well, f, who knows? F could do anything. F could be blowing up, f could be decreasing, but here, what if we assume f of t is of exponential order? You remember that discussion we had maybe, I don't know, 50 minutes, an hour ago at the very beginning where we discussed when Laplace transforms exist? One of the requirements is that f of t is of exponential order. And we said the deal with is of exponential order is that you can find an e to the minus something t that will squash the function as time goes to infinity. So if f of t is of exponential order, this here, right, the product of f of t times e to the minus st at time equals infinity, that's got to be 0, right? Because this exponent will have squashed that f term, right? Does that seem reasonable, right? We all agree on that? Great. So if f of t is of exponential order, this entire blue guy goes to 0, right? Or it is 0 at t equals infinity, right? Perfect, okay? Let's move our blue circle to examine the next term, okay? So the next term is right here, right? Okay, what does this thing look like? Okay, at t equals 0, what does this exponent become? The exponent just becomes a 1, right? Because at time equals 0, you get e to the minus 0, which is 1. So this little exponent here, maybe I'll just try to draw like this. This is a 1, right? And then I got to put in t equals 0 everywhere else. So what is f of 0? Who knows what it is, right? Because this function f, it could be doing anything, right? F of t, I don't know what this signal looks like. Maybe it does this, maybe it does that, right? Maybe it goes like this. But in this picture, where is f of 0? F of 0 is another way to say, what is the function value at time equals 0? It's the initial condition you can kind of think of the function, right? Over here, all these values are f0, right? Depending on what your function f is, right? So this whole thing in blue, what it boils down to, right, is, I don't know if I want to draw like an arrow, but I guess we can do this, right? This is basically f at time 0 over s, right? Great, okay, so tell you what, let's clean this up and let's write this thing down. So we end up with this thing becomes f0 over s plus 1 over s integral 0 to infinity of f prime of t e to the minus st dt. Okay? Great, okay, and before we get too far, maybe what we better do is, let's recall, what the heck is the left-hand side of this, right? I keep writing equals. Well, it's this over here, right? And this, remember, was just the definition of the Laplace transform of f of t. So we can write that the left side is the Laplace transform of f of t, right? Or maybe the other way you can write this, right, is f sub s, right? Okay, now if we come over here and examine this, let's examine the term here in blue. So not including this 1 over s that's on the outside, okay? I just want to examine this term here in blue. Okay, what does this look like to you? This looks like some function, you hit it with e to the minus st and you integrate time out of here, right? So if you look at this long enough, this is the definition of the Laplace transform of this function here, right? So in other words, this entire thing, right? This is the Laplace transform of f prime of t, right? Would you all agree? Okay. So if that's the case, this is awesome. This is really getting cool. Let's boil this down. Let's simplify this. So we said the left-hand side, this is f sub s, right? Is equal to the right-hand side, which is f0 over s plus 1 over s times the Laplace transform of f prime of t, right? And now, wow, we're really cooking now, because if you think about this, what did we say we wanted at the beginning, right? We said we wanted this. I want to know what is the Laplace transform of f prime of t. Here it is right here. Just solve for this thing. So actually, why don't I do it over here? Let's just solve it. Right? So what do we end up with? It is, yeah, so this is, I guess I got to move here, f sub s, right? Yeah, minus f of 0 over s, and then I would have to multiply it by this s on the other side. So actually, this would put an s here, and then this would go away. Okay. Tell you what, sorry, that was probably not the slickest way to go about it, but take my word for it. If you algebraically just solve for this term, the one we care about, right? This is what you end up with. And really, we got to box this up. I wish I had another color, but let me maybe box this up in a darker shade, because this is the one part of the differentiation theorem here. So again, we better write this down explicitly, what all these terms in the expression are, because this is very, very exciting. Okay, so in this case here, f prime of t, right, this is the derivative of an arbitrary signal f of t, right, with respect to time, right? F of s, right, f sub s, this is the Laplace transform of f of t, no f prime, right? It's just Laplace transform of the original signal f. And finally, lowercase f is 0. This is where it makes you got to be real careful which one of these is a lowercase and which one of these is an uppercase, right? This is a lowercase that we carried through, so that's what this term is. So here, f0. What is this? This is the discussion here, right? F sub 0, it's actually the initial condition of the signal in the time domain. So if f of t is like a position, if this is like the position of a block or a rocket or something like that, you're talking about the initial position of the block. How many meters to the left or the right or of your starting position are you, right? So f of t is the, let's write this down so we're all on the same page, initial condition of f of t in the time domain, right? And we better underline that, right? That's what our lowercase f notation was in contrast to our uppercase f notation, right? Lowercase meant in the time domain, uppercase meant in the Laplace domain. So this is really, really cool because what this is going to allow us to do, right, is it tells you that if you have a derivative of a signal, a derivative in the time domain appears like an S in the Laplace domain, and then you got to deal with the initial conditions here, right? So this is something that you want to burn into your memory right now, is anytime you see a pure S in the Laplace domain, it means derivative of the signal. So if you see S times something, it's the derivative of that signal here, right? Okay, this is just one level down, right? So let's go one more level down. What about f double prime, right? What if I wanted f prime prime, or the second derivative of f, okay? So let's go ahead, and it's actually not that bad. So tell you what, let me go ahead and erase some of this, and we're not even going to need that much space because you're going to see that you can actually do this proof pretty quickly, okay? So let's just do one more iteration because I think this is going to be very, very helpful, okay? What if you wanted... I now want, let's go over here, I want the Laplace transform of f prime prime of t. What does that equal? The second derivative, okay? So the way to get to this actually really, really quickly and simply here is actually, let's just go ahead and define another function. How about g of t, right? And let's just make that f prime of t. So g is just the first derivative of f, okay? So if that's the case, let's just spam this rule that we just derived here. So via the differentiation theorem, right, if I want the Laplace transform of g prime of t, right, well, differentiation theorem we just saw, if this is as s times g of s minus g0, right? That's all we're doing, okay? Well, okay, this is not that bad at all because let's just start substituting some of these things in the left-hand side. So now we have s, what is g of s? So this is, I'm sorry, where was this? Oh yeah, so this is the Laplace transform of g of t, right? Isn't that shorthand notation for what g of s is? Minus g0, right? And now, if we remember, what is g? Well, g is the first derivative of f. So we can say this is s times the Laplace transform of f prime of t. Minus, okay, here, this is now what? It's f prime at 0. And again, be real careful about lowercase versus uppercase, right? Okay, let's look at this term. What the heck is the Laplace transform of f prime of t? That's exactly what the differentiation theorem is. So let's just apply it again. So instead of it being turtles all the way down, right, it's just differentiation theorem all the way down. Let's just do it here. So now I got s times, now I got to make sure I'm careful with my parentheses. This thing is just right here, right? So this is s f sub s minus f0, right? And then I got to go minus f prime 0. Right? Okay, great. Distribute this s through. So again, you see s squared f sub s minus s f0 minus f prime 0. So here, this is the Laplace transform of g prime, which really was, well, I guess this is f double prime, right? So here you go. So here is the second derivative of f. via the differentiation theorem. And again, remember, we talked about burning this into your head. Anytime you see a derivative in the time domain, you should think s in the Laplace domain. So I see two derivatives in the time domain, so I see an s squared in the Laplace domain. And then you got to take into account initial conditions. So this is now, again, we talked about what f0 was. It's the initial position of the block. So again, maybe I shouldn't have erased this picture, but you know, maybe you got something that's doing, I don't know, this is f of t, right? So f0, again, is, we talked about it, it's this value on the y-axis, right? Okay, and now you got to take into account this term. What is this? F prime 0. This is the initial slope of the signal in the time domain. So here, this is actually the slope here. The slope here is f prime 0. So now there's multiple initial conditions here to take care of, right? So that being said, though, I think you get the pattern at this point, right? You could just keep doing this for f triple prime or f quadruple prime or f5 prime, an arbitrary number of derivatives. You just keep doing this, and pretty soon by induction you'll get the pattern, and you can actually write it out. Let me just write out what the general formula is for the differentiation theorem, because I think that will wrap all of this up nicely here. So in general, right, if you want the Laplace transform of the nth time derivative, so let's write it like this, d dt n of f of t, right? This is going to look like s to the n f of s minus s to the n minus 1 f0 minus s to the n minus 2 the first time derivative, f0, right, minus all the way down to dn minus 1 dt n minus 1 f0. Okay, so again, these are kind of shorthand notations, I guess, for take the derivative of f with respect to t first, then evaluate at time equals 0. So again, all of these are initial conditions. So all of the terms past the first term, these are all, maybe, well, I tell you, I'll draw like, crud, that was a horrible way to do this. I should have made this like a dashed line or something like that. All of these things are basically initial conditions. So again, you have an nth time derivative and you see an s to the n show up. That's the meat and potatoes of this thing here, is again, a time derivative turns out to be an s in the Laplace domain. So again, this is super duper helpful. Okay, and in fact, you know, why don't we look at an example of where this is helpful, just to drive this home.
All right, so before we do that, you know, we spent a lot of time deriving these and writing them out by hand, but you may want to be able to check your work. So I thought I would just jump back over to Mathematica to show you one of the probably the coolest functions that I think Mathematica has, and that is the function Laplace Transform. And you know what this function is going to do? It's basically going to do this Laplace Transform for you. So for example, let's go ahead and pick an f of t. Like, what was the first one we did? I think it was a e to the minus alpha t. Right? That was the original function f that we first started with, and we wanted to calculate its Laplace transform. So we showed doing it through the integral by hand, you would get a certain form. But you know what? Mathematica can check that for you. It can say, take the Laplace transform of f of t, transform it from the time domain to the Laplace domain, and what should come out of this is f sub s. So if I shift enter this, bammo, look at that. That's exactly what we had earlier, a over s plus a. And you know what? We can keep doing this. We can keep checking. Let's check one of our other f's. What was the next one we did? I think we did a step of magnitude a. And look at that. Laplace transform gives us exactly what we saw earlier. This is too much fun. Why don't we keep going? What else did we do? I think we did a ramp, right? We did, how about at, right? Here's our ramp function. Yep, a over s squared. All right, this is looking great. How about, let's keep going. Cosine. A cosine omega t. Oops. Shift enter that. And that's exactly what we got earlier. And you know what? Let's keep going. Remember we talked about how about multiplying this whole thing with a e to the minus alpha t. Right? And look at this. We're going to get that same result where you take the s and everywhere you see s, you replace it with s plus alpha. And Mathematica verifies that for us. You want to see something that's going to blow your mind? How about this? Let me clear this variable f. And let's do this again now, but now I want to take the Laplace transform not of f, but let's do f prime. So in other words, I want to take the derivative of f with respect to t. Does that make sense? So what I'm doing right here is this term that I'm highlighting right now is f prime of t. I want to take its Laplace transform and go from the time domain to the s domain, and you know what? This is our differentiation rule. So if I shift enter this thing, look at that. What does it give us? It says, here you go. This is f sub s, and then you get the s, and then you get minus the initial condition in the time domain. So it nails it for the first derivative. You know what? Keep on going. This is, I'm having a grand old time. Let's do f prime prime. So I want to take the derivative of f with respect to t twice, right? That's how I do that. So again, the thing I'm highlighting right here, this is f double prime, or f dot dot, however you want to think about it. And again, you shift enter this thing, and here we go. Here's the differentiation theorem we just derived. You get the s squared f sub s minus f prime 0, so here's the initial velocity, minus s times the initial position. So again, this is hilarious, right? Well, I mean, not hilarious. It's kind of awesome, right? It's kind of shocking that you can get all of this power out of Mathematica, and you can check all of these Laplace transforms and a lot more. So at this point, I like to think of it as we've built up sort of two versions of the function, right? We have the traditional version of the function that we're used to, the f of t, and then we have the Laplace version. It's kind of this mirror twin, right? So I don't know if any of you guys have played A Legend of Zelda: A Link to the Past on the old school Super Nintendo, but I like to think of this as the light world, right? The normal world, which is the usual way you see these functions in the time domain, and then you have this alternate dimension, or this alternate representation, which is f sub s, which is the so to speak, the dark world in Zelda. So sorry for nerding out there a little bit about the Zelda, but I think that's a very apt analogy here, where there's basically two versions or two representations of these functions. One is the one you're used to, and then one is this alternate Laplace transform version.
All right, so let's come back to a slightly varied version of the example we looked at earlier, which is, again, our classic mass spring damper system. And again, I think you've seen this so many times, I don't need to go through the derivation of the equations of motions, but I think you'll agree with me that if you've got this block translating horizontally attached to a wall with a spring and a linear damper here, and you apply a force u to it, and I want to measure the velocity or the position, or, oh, sorry, the position, that's what x is, right? It's governed by this differential equation that we obtained via Newton's second law, right? Now, remember earlier in the discussion we talked about this Laplace method for solving differential equations was a five-step process, right? And these were the 5 steps. So here with the first part, right, we start with the differential equation, which we just talked about over here. So I wrote the exact version of that equation over here just so we can kind of follow along and see how the process works for this particular example, okay? So that's the first step. So let's look at the second step, right? Usually you have the input given. So let's go ahead and how about assume that u of t is, let's just make something really simple. Let's make it a unit step, right? So again, just to refresh your memory, what this guy looks like is that u of t versus t is 0, 0, 0, and then suddenly you bang on with 1 unit of force, 1 Newton or whatever, something like that. Interesting side note, there are some funny YouTube videos of people trying to, like, for example, do a water skiing dock start where they have the boat pull them and they jump off the dock. That's just kind of similar to applying a unit step input, right? It just turns on and just goes. So I want to understand what's the response of the block to this kind of input, okay? So again, we know now the input u is typically given. So in this case, u of t is just going to be a unit step input. Okay, so if that's the case, going on to step number 3, all we need to do now is we have this differential equation, and I don't want to solve it using differential equation techniques. I want to solve it using algebraic techniques. So I'm going to apply the Laplace transform to both sides to obtain x of s and, well, I guess not really u sub s. U sub s is going to, well, I guess we can leave it like that discussion, but you'll see what I mean in a second. So what I want to do is I want to Laplace transform both sides. Oh, sorry, maybe what I should have done is I should have written, instead of u of t now, this is a 1, right? This is a unit step. Okay, so let's go ahead and write this out. So I Laplace transform the left-hand side. So this is the Laplace transform of the entire gobbledygook, right? X double dot of t plus b over m x dot of t plus k over m x of t is equal to 1 over m u of t, and sorry, I wanted the Laplace transform of that entire thing. I forgot to write that operator. So Laplace transform of 1 over m times a unit step. Right? Okay, so maybe what I'll do now is to make my life a little easier, let's distribute this Laplace operator through. Okay, so I can write this as Laplace transform of x double dot, right, plus b over m Laplace transform of x dot, plus k over m Laplace transform of x of t, right, is equal to 1 over m Laplace transform of a unit step. Great. And now all we got to do is start applying our rules of the different functions that we evaluated. So for example, this first one, this is the differentiation theorem we actually just talked about, right? It's the second derivative of a signal. So this is going to look like an s squared capital X sub s, right? And now I got to make sure I take into account the initial conditions, right? So this is now minus s times lowercase x0 minus x dot at time 0. So again, here were the initial conditions associated with this signal here, right? Now I got to say plus b over m times, okay, this term here, Laplace transform of a first derivative of a signal. So one derivative, I should see 1s in the Laplace domain times x of s minus lowercase x0. So again, initial condition, right? Plus this term right here, plus k over m, okay, and then this is pretty simple. Laplace transform of a single of the signal itself is just x of s, right? Okay, and now this equals on the right hand side 1 over m. What's the Laplace transform of a unit step? We already talked about that, so we already got that. We know that this is 1 over s, right? So there you go. Let's expand this out a little bit, and I'll shuffle things around. And if you look at this long enough, what you'll see is, you know what? There's no derivatives any longer, right? These are constants. Sure, you see a time derivative here, but this is a constant number, right? This is the initial velocity of the block. It's like 3 meters a second or something like that. Same thing with this. This is the initial position of the block. So these are constants. The thing you care about is x of s, right? I want the position of the block. So look at this. It's algebra at this point. You could solve this thing algebraically for x of s, right? Well, here, I'm sorry, I'm jumping around. Probably should have wrote, this is that garbage over there. But it's important, it's algebraic garbage. Is there a difference? There are different kinds of garbage here, but this is this term. So now we're on to step 4 where I solve for x of s using algebra, right? Just solve this guy. And I think what you end up with here is kind of an ugly expression. Tell you what, let me write it over there so we can, yeah, let's do this. So if you solve for x of s, here's what you would end up with, right? If you take that thing and you plug it in your favorite solver, you would end up with 1 over ms plus s x0 plus x dot 0 plus b over m x0 all over s squared plus b over ms plus k over m. There you go. So theoretically, like for example, like if you had an initial position of the block, so let's assume some ICs on block, right? Let's say that this thing had an initial position of -2 meters, right? So it actually started over here, so maybe it was over here, and then it had an initial velocity of +3 meters per second, right? All you got to do now is just plug in these numbers into here, and you can see also you plug in the mass of the block, the spring constant, the damping ratio, all that kind of stuff into the expression, and you end up with, at the end of the day, just an expression for x of s, right? You end up with this, right? So at that point, we're not actually done. We're going to be done for the discussion today, but because the next step, if you think about this long enough, is, okay, this is all fine and dandy that you solve for what x looks like in the Laplace domain, but really, if you were to drop this on your boss's desk and say, oh, here's what the block does, here's what it does in the Laplace domain, that doesn't really help too much, right? Because you really would like to know, what does the block do in the time domain? Like at any given time, where is the block, right? Because right, what if this thing is, I don't know, you've got a bus full of nuns or something, sitting next to it, right? You want to know, is this thing going to crash into it or not, right? So how am I going to know that if you just tell me here's what it looks like in the Laplace domain? So here's the next part, is question mark, right? And this is a little bit of a plug for our next couple videos, because this is exactly where we're going to be going on next, is once you've solved for what the signal looks like in the Laplace domain, how do I get it back into the time domain? How do I apply this inverse Laplace transform to get x of t? Because really, that's what I'm looking for at the end of the day. You always want x, right? All math problems seem to always want x, right? So with that, maybe what we should talk about real quick, maybe I'll leave you with another parting shot. If you think about this, we've basically generated a whole table or a whole bunch of different combinations of here's what a signal looks like in the time domain, here's what the signal looks like in the Laplace domain. And we did that for a ramp, an exponential, a sinusoid, multiplying by e to the at, you know, all these kind of different things. So people have done this already. So if you go out and just Google for Laplace transform table, you'll find a boatload of different relationships and different mappings here. And it's going to turn out that that's going to be one of the keys to this step here of where we want to apply the inverse Laplace transform. So I think that's a good spot to leave it, because that pretty much wraps up what I wanted to talk about today, which was how to do the forward Laplace transform, right? So if someone gives you a signal in the time domain, how do you transform that into the Laplace domain? And then we also looked at why that's helpful in the context of ordinary differential equations, because you can now turn an ordinary differential equation from a ODE problem into an algebraic problem, okay? So with that being said, I hope you'll join us for our next discussion, where we're going to take the last steps and get us back to where we want to be. So if you enjoyed the video, please hit the like button, and if you would, really please consider subscribing, because surprisingly that does help a lot in terms of making these videos. With that being said, I hope to catch you at our next discussion. So until I see you again, I'll talk to you later. Bye.